Alrighty, Tommy Reed, I want to show you exactly how big this new turbine is. And basically, if you're not familiar with the Hero engine, I'll go through that real quick. I actually have a little model I'll show you. Before the water is dripping a little bit, but I'll show you what the Hero motor basically is on this particular design. In here is basically a rotary union, if you can see that. What it does, it pushes fluid down into this is a special design pump, and I've been testing different designs. This actually has a pumping to itself, so it acts as a what they call a Worts pump, and that's a WIRTZ. If you ever look that up, they usually have them with a horizontal shaft, but this is actually a vertical. So it actually has that Archimedes screw effect inside this particular jet itself. And I just want to show you how this basically works. I got little leaks here and there. So basically what's happening is that the water is actually creating a solid thrust, unlike air. Now, if you ever look at the old sprinkler systems where the water will actually cause it to rotate, same principle. But this is very unique because the faster it goes, the pressure starts to drop, but it actually adds a little bit more pressure to it due to the design itself. So basically, the faster it goes, it's not over Unity, let's get that straight. If you ever look into the Clems engine, I'm probably the most knowledgeable in that field. And I built so many prototypes and know what does and does not work. So this is basically what I'm working on, but a bigger version with about 4 jets on it. And this is basically just a simple design. These are great little pumps. These are actually from a Prius. I think it's 2024. Great pumps, by the way. And at least it shows the concept behind it. And the thing is that even though it's not really doing any work, see, a lot of times we got a velocity of how much flow that is coming out. So when you're looking at 200 feet per second, depending on the pressure, if I start getting this up to extreme pressure, things start to change dramatically. And what happens is that it gives it even a greater thrust. Think of a water rocket. If you ever see a water rocket, you always see the air on top pushing it down and pushing that fluid out. That actually gives you double the amount of thrust than if it was just air. That's why these water rockets shoot up so high. You can't do it with just compressed air, especially at 100 psi. So it gives you, depending on the nozzle too, would depend on how much thrust is generated. So on this particular one, right now I'm working on some numbers. This is going to have 4 independent jets, and basically it's going to across. But this is actually a very unique design too. This is actually a water turbine, but also a Pelton turbine all in one. So what it does, it has on the outer rim, there is the Pelton blades, and basically they actually rotate in the opposite direction. And the reason is that once you get thrust going at full power, that Pelton wheel will not turn because now it cancels out. That's why you have to put it under a load. So, for example, if I put it under 1,000 RPMs and I break it down to 1,000 RPMs is the top speed, but I have no torque. So if I bring it down to 500 RPMs, whatever my thrust is, it'll be half of that total thrust itself. If it's at stalled, it'll be the maximum. But at that 500 RPMs, guess what's happening? It's also now pushing on the Pelton wheel, causing the Pelton wheel to go in the opposite direction. So it actually is 2 turbines in one. And the unique thing is the distance from the center shaft, it's going to roughly be about 9 inches. So that's pretty much almost like 3/4 of a foot-pound per nozzle. So basically, if I have 4/16 of an inch orifice, it's going to produce about 20, I believe it was 28 pounds of thrust at 1,000 psi. Now, that's only the stall thrust. But when you calculate it by the, 0.75, because it's about 9 inches from the radius, it's going to be roughly around 21 foot-pounds of torque. But that's at a stall. So at a certain amount of RPM, depending on the pressure, will depend on the amount of RPM. If I cut that RPM in half, I will actually get about roughly, probably around 16, no, probably around, I believe around 15, almost around, I'm sorry, about 11 foot-pounds of torque, which is good, even at the RPMs. So it gives you a pretty good idea. And I'm working on this. This is a very tricky design, and I have to have a rotary union, and what I have is the mother of all rotary union. I actually got this. I kept it. This is probably worth $1,000. It is a reverse thread, 1 inch, which is not a problem. I have to thread that for a special fitting for it. And this is my main. This is going to go down on the lower end, and this is going to be my main input. And basically, that's going to shoot up into the rim jets. That's also going to have a 1 inch shaft to it. So think of here's the rim jets, basically. I'm going to have a shaft up top, and then I have my bearings and sandwich this together. And all the flow has to go down into a reserve. So I have another tank here that I will cut open so the fluid actually drains down so I can pull it from the reserve. So it's a closed loop system. And even though I'm leaking here, you can see that this is still working the way it is. Now this is like no pressure. If I put 100 PSI in this thing is going to run like a bat out of hell because it's going to be very fast. And there's a flow rate. If you're pulling so many feet per second, you can actually calculate how fast the top speed would be by the circumference of the rotation. So pretty much the math isn't that difficult. The thrust can be very tricky because you got 4 jets, you got orifices, and the amount of gallons per minute. And I believe the rough figure was about 12 gallons per minute with 4 jets at 1,000 PSI. Roughly. I know I looked at the formulas before, so it gives you a pretty good idea. But the good thing about it, when this starts to rotate, it does a lot of amazing things because it has the counter rotation going on. That means this is going, say, clockwise. This is actually going clockwise, and then the Pelton wheel is going counterclockwise. So I'm getting both of the amount of power out of each of them. So it gives me that potential of kinetic energy. I can convert that into electricity. This is a little bit more complex than the other one. And in fact, to give you the idea of the size, this was the tank I used. Basically, I bought a brand new air compressor. It was like $99, and I wanted the tank. And just to show you the difference in size, and this was only 6 inches in radius. This is going to be about 9 inches of radius, which gives me even more torque. But this only had 2 jets. This one will have 4. And we have the 16 gallons per minute pump that we can use. So that gives you a pretty good idea. If you're not familiar with a Hero engine, this is basically what it is. At the first one they developed was actually, they put water in and converted it into steam. This is actually just using direct thrust, like a water jet, but at a very high pressure. So I hope you understand what this is all about. I got some work to do, getting this up and running. Doesn't take me long. I'm very good at fabricating. Been doing it for a long time, but it gives you a pretty good idea of the simplicity of this whole design. So Tommy Reed, I hope you enjoy this video. Bye-bye.